Hello, everyone, and welcome to Encompass University Live. So, for those of you who were with us last year, you may remember that we did a monthly class with Encompass. And this year, we're doing the same exact thing again. So, luckily, we are back into that kind of swing. We had a few months off, and now we're back in, and we're doing a whole new training plan over the course of the next 12 months, well, until December. So last month, if you haven't watched it, go back and watch last month's class, and it's right on this YouTube channel, and it is on HVAC safety, and it's a super important class. I always try to do it in the beginning of any training plan because it is the most important thing. We don't care about anything in the trades more than we care about your safety. So if you haven't watched that one yet, if you're concerned that maybe you're not sure of all the safety rules and regulations or what you should be doing on site, make sure you go back and watch that. For today, we're going to go over heat transfer and the refrigeration cycle. So heat transfer in general, in physics, in the real world, and then how does that apply back to our air conditioning units? That's what we're going to start with today. I'm going to go ahead and share my screen. Today, we are going to do a slideshow. Normally, I don't like to do slideshows. We will be probably back on the whiteboard next month for our next session, but I have a really, really good slideshow on this, and I want to make sure that anybody in HVAC, anybody learning HVAC, we have a lot of appliance repair technicians on this channel that may have dabble a little bit in HVAC, but they don't get to do it all the time. And so it's really hard to learn specific things about HVAC when you're not going to trade school for it, or your job maybe teeters on the edge. So that's why we're doing this. And this presentation has a lot of really great information that will absolutely help anybody in HVAC or coming into HVAC to be able to understand heat transfer, the refrigeration cycle, and then how that correlates to what you see on your gauges. If you're hooking up gauges to a unit, you need to be able to read temperatures and all these things. There was a day when we only read pressures for the most part, and then we would calculate, our superheat, our subcool, and our saturation temperatures. Now we have these amazing tools, this amazing technology that just continues to outpour into our industry. And those amazing tools should be used, right? So now we have digital gauges that tell us what all of that is, what calculate those for us. So now we have to get into the mindset where we know how to read them. We know what each temperature and each pressure correlates to when it comes to the refrigeration cycle. Unfortunately, in 20 years ago, 10 years ago, even in trade school, we didn't have comprehensive learning about that because we didn't have the tools we have today. So even if you're a 40-year technician, even if you're a 6-month technician, it doesn't matter. Everybody needs to get back to the basics of the refrigeration cycle because we never knew back then, back when some of you went to trade school, that we were going to be looking at all this new technology, or that we were going to be able to further diagnose beyond the pressures, right? Or beyond beer can cold. We didn't know we were going to be evacuating units even. So now it's time to learn all that juicy stuff that we didn't get in trade school. And luckily, Encompass has, poured so much back into this community by hiring me to be here to teach you. So I'm going to go ahead and share my screen. We're going to get right into this. If you put questions or comments in the comment section, I will see them. I will just see them after the slideshow. So we'll save a few minutes at the end to be able to go over those. And again, thank you guys for being here. Make sure that you shop Encompass. We have Easy Stock at Encompass. I will never stop talking about this enough. There is a app that Encompass puts out there. That's a free app. It helps you to maintain your inventory. So if your truck, say you have 20 capacitors on it, and you need to know which capacitors, right? You can scan all of those and you can put them all into your inventory on the Easy Stack app. And then you can go back, and every time you use one, you can scan that too. And you can let the app know that you've used one. By the end of it, you have the app letting you know that you need to restock your inventory, which is really awesome. I just thought that was very cool. You can also order parts right through that app, which is awesome. All right, gonna go ahead and share now. And I keep saying that, but I'm really gonna do it this time, guys. Here goes my screen. All righty, Roo. So again, you guys, I won't be able to see your comments while I'm in the presentation just because of the way that I do it, but I will absolutely get to your questions and comments after. Please don't hesitate to leave them in the chat just because I won't see them right off the bat. So today we're going to talk about heat transfer and refrigeration theory. And anybody who's been in this trade for a while knows that they are exactly the same thing. We are essentially using heat exchangers to move heat. We're not necessarily blowing cold into a room. We are removing heat from that air, and then we are recirculating the air that already had the heat removed. So that's important to remember. when we're talking about this, when we're talking about heat transfer in air conditioning. So every air conditioner has 4 main components. There are actually 5, and we will talk about that as we get a little bit further. But if you know what the 5th component is that I'm talking about, please put it in the comments. These are the components that every single refrigeration unit has. So every type of walk-in has these components. Every type of air conditioner has these components. They're universal, right? So that's why we call them the 4 major components. But there is a 5th one that they all also have that is not talked about as much. So if you know it, please put it in the comments. If not, I will give you the answer to that at the end. So let's get into them. The first one I always start with, because it's kind of central to the system and it just kind of is the most important to me, I guess, is going to be the compressor. And the compressor's job is just to take vapor refrigerant and compress it. It is going to superheat and super pressurize that refrigerant. It's always vapor. It's going to come into the compressor as a vapor and it's going to leave the compressor as a vapor. Then we'll skip down here to the metering device. These are equal and opposite, you guys. This is a cycle. And if we think of it as 2 halves of a whole, right? We have one side over here and we've got one side over here. So if we go equal and opposite of the compressor, we get the metering device. And what the metering device does is removes the pressure. And thus, in removing the pressure, we're removing the temperature because they're the same thing, right? So where the compressor adds pressure, the metering device removes it. And what that does is turn it back into a semi-liquid, semi-vapor state. We will talk about that on the next slide, but that's what it does. It removes the pressure and allows it to move through the system, through the other side of the system. Now, when we get to the condenser coil and the evaporator, it's the same thing. It is equal and opposite components doing the same job, but opposite. So we have the condenser coil, which job is to condense the refrigerant back into a liquid, whereas oppositely, the evaporator's job is to evaporate it into a vapor. And that ensures, both of these 2 components ensure that this compressor does not see liquid as long as we have a correct charge, we have correct airflow, and the system is working properly. You should not ever have liquid in a compressor. Some people are under the misunderstanding that a compressor is a pump of some sort, or they'll call it the motor. And when we call it things like a pump and a motor, it removes what it actually is. It takes away the actual job, the work, the thermodynamic work that the compressor does. It compresses. It does not pump. So therefore, it has to have vapor only. So those are the 4 main components. The 5th, you guys, is a thermostat. We can't do anything with any of these components if we don't have a way to control them. So a thermostat is 100% necessary. Therefore, it should be the 5th component. But when we look at textbooks and we look at, the teaching of the past, we don't talk about the thermostat as being a major component. It has to be, because we cannot turn any of this on without a thermostat, unless we're just jumping out boards over here, which we don't want to do. So now we're going to jump in a little bit into heat transfer, and we are going to get back to the refrigeration cycle as this attributes to it. But I really just want to talk to you about the different types of heat transfer first, because it matters. When we're talking about air conditioning being 100% heat transfer, we need to know what kind. And then when we get into the heating side of things, we're using this even more. So convection is going to be the transfer of heat from one region of a fluid to another due to movements within the fluid called convection. So as we put that, we'll use water for this situation just because it's the easiest one to really understand. When we put water in a pot and we put it on a burner, right, we are heating that water, but all of that water does not heat at the same time. So we're heating the water closest to the source first, and then the movement as water heats, as anything heats, it vibrates. And it vibrates faster and faster and faster and faster the hotter it gets. So by the time it's at its hottest point, boiling, right, 212 degrees of water, we can't go past that. Once we are at 212 degrees when we're boiling water, we are now changing phase. We're no longer boiling water past 212 degrees. Any water that is under 212 degrees is not going to be a saturated vapor. Any water that is above 212 degrees is no longer water. It's a vapor. So when we're talking about convection, that vibration is what transfers the heat. So because those molecules are moving faster and faster and faster to try to get away from each other, thus becoming vapor, that the water that is still in liquid form is going to move. And that flow of movement is what causes the heat transfer. So how many times have you run a bath for your kid, right? And it's a little bit too cold. So you add some hot water and then you take your hand and you kind of mix it around. So convection is essentially that flow of water attributing to the heat of the total of the whole. That is convection. Conduction. The movement of heat within an object is called conduction. Conduction also occurs when objects are touching. So if this pot, right, if this pot is on top of this burner, it's definitely going to have some conduction. Even more so when the pot is hot, and this is the best example, when the pot is hot and it touches the water, that is conduction heat. When your handle gets hot because the pot is hot, that's conduction heat. It happens when two things touch, right? So if you grab your hot cup of coffee off the table and your hand is cooler than the coffee, heat is going to naturally migrate to whatever is cooler that's touching it or that's near it. And so because of that, your hand is going to take on conduction from the cup. So as you put your cup in your hand, the cup transfers some of that heat into your hand, into the object that's touching it. That is conduction. Radiation is the last real defined method of heat transfer. And again, you guys, this is not like end all be all. There are parts that are in between. There are situations where you're using all three to transfer heat, but these are the separation that we go by. So the radiation is going to be the transfer of energy through electromagnetic waves. So if I have this electric burner under my pot, and it is pushing heat away from it, right? Because heat goes to cold naturally. If my pot is cooler than the hot burner, it's going to transfer that heat into the pot, all at that time, doing so via electromagnetic waves. So what is radiating off of something? When the sun shines down on you and those rays of sun make you nice and warm, that's because of radiation. It's radiating warmth onto you. Those are the three major methods of heat transfer. So keeping that in mind, we're going to kind of go a little bit more into this heat transfer thing and about warmer objects going into cooler objects, but we're going to do it from a refrigeration standpoint, from an air conditioning standpoint anyway. So as you can see, warmer objects naturally transfer their heat to cooler objects, and we can't stop that. That's physics. That's something that we have to work with, not against. So if a room has hot air, okay, say my room is 85 degrees and then my air conditioner kicks on. And now my return vents are sucking in that 85-degree air. They're taking that air and they're passing it past my evaporator. And now a perfect evaporator is going to be around 40 degrees. So if I have 85-degree air and it's being passed via the return over the heat exchanger, in this case, that's going to be the indoor coil. If the indoor coil is 40 degrees, it's going to transfer that heat to that coil, to the copper and into the refrigerant. So that heat that's coming in from the room is going to not blow colder. It's going to naturally have less heat. So as the hot room air comes in through the return and blows over the indoor coil, it's going to settle into those refrigerant pipes. When it settles into those refrigerant pipes, the refrigerant is the coldest part. So the refrigerant is going to grab that heat and it's going to travel it all the way through its line and into the outdoor unit. When it gets to the outdoor unit's job is to reject that heat. So typically, not every day and not everywhere, but typically for the most part, as a rule, the outdoor air is typically less hot than the air coming out of the condenser. So if I have 110-degree air coming out of my condenser, it might be 90 degrees outside, but at least it's cooler, right? So that's going to have natural heat transfer where it's going to naturally go to the cooler temperature, but also I'm helping that along by blowing that heat and rejecting that heat out of my condenser. And so this is air conditioning, right? So the conditioned air goes back to the warm room via the supply ducts. After we've passed it past the evaporator coil, after we've rejected the heat out of the condenser coil, now that same air, not new cold air, but that same air that we removed the heat from is going to blow back into the room via the supply ducts. And that is air conditioning. That's what that is. Once the room is cooled down to set point, it'll shut off, right? Because we don't need to do that. We don't need to complete that process anymore. And once it starts to rise again, it'll kick back on and start that whole process all over again. So in this process, surfaces are cooling too. So now we're seeing just about every method of heat transfer, all because of air conditioning, that surface cool. So your room is cooler and now your table is cool. Say the coffee table in your room is cool. So you set your drink on that coffee table in your nice cool room, and it's going to pull some of that heat out of your coffee cup into the surface, right? This is a good thing, except in situations where we might have an oversized air conditioning unit or an overcharged air conditioning unit, a unit that is not running enough, that is short cycling. In that case, in high humid areas, we might have lots of humidity in the space. And it depends on infiltration, envelope leakage. Is there, is it an older house that doesn't have great insulation? These kinds of things all play a factor. But if we have high humidity outside that is being brought into the house via cracks and depressurization and all these things, if we have that humidity coming in and then we're cooling that air too quickly, but we're not running long enough to dehumidify, that's when you end up with, like, you'll see supply registers, or even sometimes a return, more typically the supply. You'll see lots of condensation on it. You'll see black mold forming. You'll see growth forming throughout your ductwork. You'll see that your windows are fogging up every time your AC kicks on and off. These are all signs that you are not conditioning correctly, and there are many reasons for that. Some are, again, the envelope, and some could be the unit. But those are things we need to watch for, because if a unit is running, it is dehumidifying, or it should be anyway. All right, so let's move back, I guess, to the basic refrigeration cycle. Now, knowing what we know about heat transfer, let's walk through what our air conditioner is doing. How is it using that heat transfer in order to condition a room? So we'll start at the compressor again, just because consistency is key. When we start at the compressor, what we'll notice, the first thing we'll notice, this is a really great graphic that was provided to me by AC Service Tech, and we are so grateful at HVAChick for the use of these graphics. If you guys don't watch AC Service Tech, please go and look him up on YouTube. He taught me everything I know when I got into this trade and was thrown to the wolves. So please check that out for your own benefit. So what you'll notice on this graphic is that coming into the compressor, we have this kind of light blue dotted kind of vapor. And then out of the compressor, we have this red kind of dotted vapor. The key is that both sides are vapor. So we have into the compressor a low temperature, low pressure vapor coming into the compressor. The compressor adds pressure to it. It compresses that vapor refrigerant. And what it spits out is a high pressure, high temperature vapor into the condenser coil. So as we look at this, just with visual eyes on it, the first thing we should notice is that both sides are vapor, and that is because a compressor cannot compress liquid. We never want to see liquid in any circumstance. So, and I will walk you through what happens when that happens, or why we could get liquid in our compressor as well. But for right now, we're just going to talk about what happens in this process, okay? So in comes our low pressure, low temperature vapor. Out comes our high pressure, high temperature vapor. Through our condenser coil, we can notice this phase change. So the condenser coil isn't creating a phase change necessarily. That's the compressor's job. The compressor's job is to make sure that a phase change can occur, right? So once we get to the condenser coil, as you can see, halfway up this condenser coil, we're going from mostly vapor to mostly liquid. And by the time we're exiting that condenser coil, we are completely a liquid. We're 100% liquid. So what's going to happen here if we have too much refrigerant in the system is that this phase change will happen somewhere closer to up here. It won't happen the way it's supposed to. You will have way too much liquid in your condenser, and that's going to stop our ability to reject heat. And we'll talk more about that. But just so that you know what I'm talking about here, we have a vapor coming into the condenser coil. The condenser coil provides surface area. That's really all it does. It doesn't have any mechanical moving parts. It's just the condenser coil itself is just surface area. So you'll see on a condenser coil all those fins that love to grab all that dirt and nasty leaves and all those things. We have to clean them constantly. Those fins are so important. And the reason that causes such a problem when they're dirty is because we need every bit of surface area that we can get in order to allow this phase change to happen. So in a perfect unit, which is what you're seeing on my screen right now, in a perfect unit, that change will happen somewhere about halfway to where we're saturating as a liquid. So we'll talk about saturation more in a minute too, after we get through what the cycle does. You can see a liquid service valve here. This is not considered a component, and that's because all it does is allow us to access inside the system to test. It does not create any change within the system. It's just a flow through. So even though it's a service valve on this side where we can hook up and we can, manipulate it a little bit, going through that valve for the refrigerant itself is just a pass through. And then the same with the filter dryer. Some units have filter dryers, some do not. The reason we have filter dryers is because now, not so much. Now we're talking about that new technology and all these new things we're learning. And now we know we need to do things like pull and evacuation, right? We want to pull down to 200 microns. We want to decay test to 600 microns or less, and then we're going to be okay. But for the longest time, it was no evacuation at all. It was just dumping the charge into this dirty, wet unit. And that's how it went for a very, very long time, decades. And then we got a little wiser and we created vacuum pumps and recovery machines and all these things. And then we ended up pulling down to 500 microns, which is actually in the EPA test and is no longer correct. But 500 microns decay to 1,000 microns and then dump the charge. Now we have the capability to go so much lower than that, and we really need to be pulling as deep a vacuum as possible. And if anybody's ever told you that if you pull too fast of a vacuum or too deep of a vacuum, that the water molecules will freeze within the system, it's possible under certain circumstances, but it's not widely possible. You do not need to worry about that. Pull as deep of a vacuum as you can. So anyway, when we weren't pulling vacuums, when we weren't brazing with nitrogen and we were creating all this oxidation on the inside of our pipes, it was very necessary to have a filter, to have some way to filter all of that gunk out before the metering device. Metering devices clog very, very easily. It is not hard to clog them. So anything we can do to try to stop that from happening is super, super necessary. So they created the filter dryer. Parker Sporlin actually created it. So inside this filter dryer is a level of desiccant. So desiccant is a filter material that holds on to any non-condensables, any air, any dirt, any moisture that's in the system, and doesn't allow it to pass through the filter dryer, but it does allow clean refrigerant to pass through the filter dryer. So even if you do have a filter dryer, it's not a component. It's not considered a major component anyway, but it is just a pass through, just like a service valve would be. So now after the condenser coil, we're in total liquid form. We are a high pressure, high temperature liquid. We are cooking over here, and we are blowing that right down the line to the metering device. Now, the metering device has only one job as well, but it's equal and opposite of the compressor. Metering device is going to release that pressure. So now what's going to come out of the metering device, even though we have 100% liquid going in, what's actually coming out is about 20% vapor and about 80% liquid. And that's going to be a low pressure, low temperature liquid mixed with vapor. And the vapor is just a byproduct, right? Anytime we remove the pressure that quickly, we're going to end up with some vapor because all of those molecules, again, are so hot that they're moving. So a byproduct of metering refrigerant gives us 20% refrigerant and 80% liquid, basically. It's in that range. So then we enter the evaporator as a 20% vapor, an 80% liquid. In that evaporator, it's doing the exact equal and opposite job of the condenser. So where we were providing a lot of surface area over here, as much surface area as possible to allow phase change to occur naturally, we're doing the exact same thing over here in the evaporator coil. It's just the opposite. So where we were changing to liquid, now we're changing to vapor. So on a perfect system, again, about here, we're getting saturated as a vapor, and then we're traveling through all those coils, and we're taking the surface area from the fins, and we're transferring that heat again to change phase. Now, as we come out and exit the evaporator, we are a low pressure, low temperature vapor. So as we come back up this way, we should only be vapor. Notice there's no 20% liquid. There's no liquid on either side of this. Coming back into the compressor as a low pressure, low temperature vapor. And now we've completed the cycle. Now there's other things happening. We can definitely transfer, we can move some heat with this process. But we can move a whole lot more if we add some fans into the ordeal, if we take care of our airflow, right? So what's happening as far as airflow goes is the condenser fan is spinning, the motor is spinning the fan is rejecting heat, it's taking all of that heat out of the refrigerant that we have now turned into a liquid. So as we remove the heat from the refrigerant, it turns back into a liquid. It's just a natural process. So again, condenser coil, it has no moving parts. It's not doing anything other than providing surface area. Now, the fan is another story. The fan is rejecting that heat to the outside and removing it from the refrigerant. So whereas the evaporator grabs the refrigerant or the heat from the room, the condenser does the opposite. It gets rid of the heat out of that refrigerant. So condenser fan blows the heat, rejects it outside where it is not there to make anybody sticky or sweaty or swampy, right? At the same time, outside air is coming into the condenser coil and it's helping with that phase change because it's, again, cooler usually. Sometimes we have situations where our condenser is rejecting heat that is cooler than the outdoor ambient temperature. But for the most part, we have cooler air. So what's that going to do? That's going to aid in that heat transfer too, via a different method of heat transfer. So we have this fan that's helping us along. We have natural physics helping us along. And then we're moving those natural physics even deeper by having that outside ambient air cooling that refrigerant as well. So then that's what we're doing with the fan on the outdoor coil. We go back to the indoor coil and we have a blower motor. That blower motor is responsible for pulling air via the return. Okay. So where's our air inside? Okay, we'll call it this, right? So this blower is taking room air. Yep, that's our return air in. Okay, so if we're taking air out of the room that is 85 degrees, this blower is blasting it past this evaporator coil, right? That evaporator coil is removing the heat from that air and sending it again through the cycle. Once it is out of the room and across that coil, it's not our problem anymore. Now we're blowing in that same air. Remember this, we're not gathering new cold air from somewhere and blowing it into the room. We are taking that same air we remove the heat from, and then we're blowing it back into the room via the supply. So that's really important, guys. It's so important that we not only have a great refrigeration cycle happening and that we have a proper charge to max out that great refrigeration cycle, but the airflow is so, so, so important. And unfortunately, as technicians, it tends to be the thing we forget the most. And so if we see things on our gauges, like, where should we start with this? So if we see things on our gauges, like our evaporator temperature, and this one that is on the page, honestly, would probably be right around 40 degrees, which is our perfect AC evaporator temperature for the moment. So if this evaporator is 40 degrees, okay, I can tell that this phase change is happening how it should be because I know that my design vapor saturation, my VSAT, is 40 degrees. So if I'm close to 40 degrees, I know this phase change is happening where it should be in the coil. And I know for a fact that vapor refrigerant is going back to my compressor because I wouldn't have a 40-degree evaporator otherwise. Now, that's in a perfect world. And anybody that's an HVAC tech watching this, you're gonna be screaming at the screen right now, being like, yeah, right, like that's gonna. So yeah, it does happen in the field, but more often it's not correct. Something is happening. That's why we were called there, right? So if I instead were to see, say, a 57-degree evaporator, if I see a 57-degree evaporator, I can definitely tell that this phase change is going to be happening closer to my outlet. Now, my outlet goes directly to my compressor. I do not want liquid there, but it happens so often because we don't know how to read our temperatures. We don't know what our temperatures mean. So if I now know that a 40-degree evaporator means that I am changing phase in the correct place, and I know that anything above that means that I'm changing phase way up here, so I have more liquid than I need, and I know that anything below that means that I'm changing phase down here and I have not enough liquid, that can tell me so many things just by looking at my gauges. So if I look at if I have, say I have a call where my unit is not keeping up, that's the customer states call. Unit's not keeping up. It's, 80 degrees in my house right now. And I show up and I find my evaporator temperature at 20 degrees and a block of ice. Well, then I can pretty much surmise that that's why I'm not blowing very much cold air. And because I'm only using half of the cycle, right? I'm not able to remove heat if I'm a block of ice in my evaporator. Now, on the flip side, if I find that evaporator at 57 degrees, I can surmise that I either have an overcharge, I have too much refrigerant in the entire system, or, sorry guys, jumped the gun there, or I have some sort of weird suction line restriction that is filling my evaporator. We won't get into all the nitty gritty of crazy things that can happen because I have seen it all. But for the most part, you're going to see a frozen evaporator. Now, there's a couple reasons for that. If I see a frozen evaporator, I can surmise that I don't have enough refrigerant. That would be a great, a great thing to draw from that. But I need to look at both sides of the system. So another thing that could be happening is I look at my gauges and I have a low condensing temperature and I have incorrect subcool. And what's actually happening is that my condenser coil is flooded. So if my condenser coil is flooded and my evaporator coil is empty, that only leaves this kind of area right here. That says I have something completely blocking off the flow of refrigerant from my condenser coil to my evaporator coil. That's what we call a restriction. Most of the time it happens in the metering device, but it can happen anywhere on the liquid line. So if I show up and I have, that 20-degree evaporator, it's a frozen block of ice, but my condenser is also full of refrigerant, I do not want to put any more refrigerant in this unit, right? Now, what if I walked up on that exact same unit and I looked at that low evaporator temperature and I said, my evaporator's empty, which means my system's low. And then I just put some more refrigerant in it. Well, at that point, my condenser is already full of liquid refrigerant. It's already holding as much as it can hold. So what's going to happen is it's going to fill with more liquid refrigerant. That only has one place to go, which is directly to the compressor. Now, a lot of units, especially inverters, a lot of the new units now that we're seeing, a lot of refrigeration units as well, have accumulators or receivers. So those will help a little bit if we have an overcharge situation. They'll help to keep that liquid out of the compressor. But in the majority of units, they're older. They don't have those. They're not for refrigeration. They're for AC. And so instead, that excess liquid that we just jacked into that system that wasn't low to begin with now ends up back in the compressor. That compressor tries to pump the liquid. It can't. It eventually breaks a scroll, or it acidifies, or it ends up having complete burnout. So we really need to make sure that we're not only looking at one thing. When we look at our gauges, we want to make sure that we're looking at all of these little clues. It's like a puzzle, right? We've got all these different puzzle pieces. We've got vapor saturation, liquid saturation, condensing temperature, evaporator temperature. We have our compressor pressures, right? The other thing is you could show up and have all these crazy weird temperatures and be like, what is going on here? And I actually did this the other day. I got such tunnel vision on a unit that somebody sent me a picture and I didn't even look at the pressures because I'm so used to the pressures not mattering to me. I'm so used to it being a diagnosis that I need temperatures for. So I didn't look at the pressures. And if I had, I would have realized that they were 128 and 158. They were pretty much equalized, which means my compressor was not working. My compressor was junk. I could have told that in 5 seconds if I had looked at every piece of the puzzle instead of just the ones that I'm used to looking at. So we really want to make sure we're taking all those puzzle pieces and putting them together. Now, one puzzle piece is going to be your airflow. We need to be testing that. We don't want to say I have good airflow. We don't want to put our hand, over a register and say, yes, it's blowing, so I have good airflow. We always want to test. If we're not testing, we're guessing. You want to be using psychrometers. You want to be using thermometers. K-type thermocouples are great if you want to test temperatures at different places and you just have meters. You can use those to do that. There's all kinds of ways that you can test, but the important thing is that you are testing. We need to know how much CFM we have through our ducts in order to make sure that airflow is not what's emptying our evaporator. We want to make sure that our filter is not restrictive. So we want to take, static pressure readings. Do we have a blockage in the duct? Do we have ducts that are too small? Do we have a restricted filter? Do we have a dirty coil, indoor or outdoor? There are so many things that can cause this that we need to really make sure we're looking at the full picture. So then we talk about, just real quick, we talk about superheat and subcool. Okay. So superheat defined, the definition of superheat is going to be the temperature at which we are above saturation point. So in the evaporator. So in the evaporator, if we are saturating at 40 degrees, say we're saturated as a vapor at 40 degrees, okay? And we have 10 degrees of superheat. All that's telling us is that 10 degrees more than saturation is what our unit is running at. And that's really important because if it's high, that tells us our evaporator is empty. That gives us another clue. So if we have low evaporator temperature and high superheat, that means that we're not saturating at the correct spot. That means that we are very, very low on refrigerant for one reason or another in the evaporator. So again, two puzzle pieces that are given directly to us on a silver platter that we can use together, but using them separately might not be a great idea. So then on the flip side, subcool, same thing, but opposite. So subcool is the temperature at which we are below saturation temperature, because we are removing the heat from that substance. That substance is turning into a liquid, which means it's cooler, right? So we need to know how many degrees below saturation is my subcool. And that's what that's going to tell us. All right, moving along a little bit. And you guys, if you have questions, comments, anything to add, please put it in the comment section. I will absolutely get to it as soon as this is over, but I just can't see both screens at once the way that I do this. But please don't hesitate to put it in there thinking I won't get to it, because I absolutely will. All right, let's take a little break from that for a second. Phase change. Which two components change the refrigerant phase? The answer to that is going to be the metering device and the compressor. Now, everybody here just wanted to scream the evaporator and the condenser. Why? Because that's the point at which in the system, that's where the phase change takes place. But that's not what's changing the phase. What's changing the phase is adding and releasing pressure. And we only do that in two components. Those components are the metering device and the compressor. What phase change happens in the condenser? So what phase change is happening at that point in the condenser coil because of the compressor? What phase change is happening? We just went over that completely. So we're turning back from a vapor to a liquid. What is the job of the metering device? The opposite of the compressor. We're removing that same pressure that the compressor just added in order to turn into a cold liquid. And then we're going into the evaporator. We're turning back into a vapor. Phase change is happening, right? And it's happening all over this system, but there's only two components that cause it, that are the reason for it. Now, I like to add this in. It's not super important for what we're doing right now, but there probably are a lot of restaurant techs that watch these, especially for Encompass. So I just want to go over it very, very quickly. So in the residential world and in the commercial world, we'll see a lot of heat pumps. If it's a heat pump, it has a reversing valve, okay? That reversing valve is solely responsible for deciding which direction the refrigerant flows. So it's going to be the first component that our refrigerant comes to after that disconnect is turned on and that thermostat is calling. It's going to go directly to the reversing valve. And this solenoid is electrically powered, and it's going to talk to the thermostat. It's going to talk to the unit. It's going to talk to the outdoor ambient temperature. It's going to be either energized or de-energized on cooling or heating, depending on the brand. And what it's going to do when it's talking to it is it's going to say, the thermostat's going to say, hey, homeowner just switched this into heat. We need to change the direction of flow. So it's going to slide from here. It's going to slide the internal valve body over in order to allow that flow out of the correct pipe. So whether it's heat, it will go down one pipe. If it's cool, it'll go down another pipe. But that's the first place that it stops. Well, that's the first place that it does anything. Okay, it's just flowing otherwise. Once we get to the reversing valve, we're deciding, are we reversing that entire refrigerant cycle to heat this room, or are we letting it go in the normal, typical physical way? And that's the component that decides it. But what's interesting is that's done by solenoid valve. So it's not very different from a walk-in cooler, right? So a walk-in cooler has a liquid line solenoid valve. What that does is, we won't even say cooler. Let's talk about a freezer, okay? Just because it's the best example. So if I have a -20 cold room with a Trenton evaporator in it, okay? And I leave, say it gets down to set point. It gets down to -20 degrees in that room. And I leave the refrigerant in the evaporator coil, okay? What could happen is now we are dangerously close to the dew point and to not bubbling off any refrigerant at all, which means the refrigerant's not going to be moving because we're not using the unit. So if this unit is shut off, it's at set point, and that refrigerant is just sitting in the pipe, that refrigerant could freeze. It could continue and continue and continue to get colder and colder and colder until the refrigerant molecules freeze. Now, what's more likely going to happen is we're going to build up ice on the actual coil, on the fans, on the unit. And because the refrigerant is still sitting there, it's just going to make it colder. And we will have a hell of a time getting the ice off of that unit. And that when we have ice buildups, like between the coil loops, you end up breaking them. Those coil loops will spring leaks. The ice will build up between them and spread them apart. And in that case, we're just putting holes or cracks in those coil loops. We don't want that. So in refrigeration, when we need to go down that cold, what we're going to do is put a liquid line solenoid in. And when we put a liquid line solenoid in, it opens and shuts. So if we have a call for cooling, that solenoid is going to open. It's going to allow the flow of refrigerant from the condenser to the evaporator. It's going to complete the refrigeration cycle as many times as it needs to in order to cool the room to set point. Once set point is reached, it's going to empty the evaporator and it's going to close that liquid line solenoid. It's going to stop refrigerant from being able to sit stagnant in the evaporator. But what's interesting again is that it's the same component on two completely different machines for two completely different reasons. And that's because they're very simple. It's a simple way to control the flow of refrigerant, but that's also because that's what it's doing. It's controlling the flow of refrigerant. No matter which application you have it in, that's its job. Oh, let's see if we can skip here. All right, so just to sum that part of this up, and we're going to go into a couple of other things just because they're fun, but just to sum it up, Nick Cage is over here with his hair blowing in the wind and his nice cold AC. Superheat occurs when you have heat, when you heat vapor above its boiling point. So however many degrees above the boiling point, that is how many degrees of superheat. Subcooling, equal and opposite, occurs when you cool vapor below its condensation point. So at whatever point it's condensing, whatever degrees below that we have is going to be our subcool. That's going to be how many degrees of subcool we have. They indicate whether vapor or liquid is being sent to the compressor. Now, most things, you guys, most things in an air conditioner are specifically designed for the sole purpose of not allowing liquid into the compressor. And that is how important this is. So if we get into a habit where we don't know how to read our gauges properly and we're rushing because our boss is on us, we need to get, 10 service calls done today because we're just slammed. You're going to be here till midnight. And you accidentally misdiagnose a restriction for a undercharge, right? And so you gas and go it. You put some more refrigerant in it. Makes perfect sense, except that now you have flooded that compressor, and now that compressor is not going to last. It's going to die. And compressors do not die on their own. They're murdered. And that is the number one way that they're murdered, is by flooding them with liquid. So again, if you have, depending on what your subcooling and your superheat is, that is indicative of how much vapor or how much liquid is heading back to the compressor. ACs cool a room by removing heat and releasing it outside. Again, we do not have this hidden, behind the curtain of Oz source of air that is freezing cold that we can just blow into a home whenever we want to. We have to use the air we have, which typically is not cold at all. It's hot. And the way that we can make it cold is by removing the heat, rejecting the heat outside where there are no people or where people aren't going to be affected, and then putting that same air back in. And then what happens? We do it all over again. So we may not get our air from our supply down to 50 degrees the first cycle that it goes through because we can't remove all of the heat at once. So what happens is we have 80-degree air, we pull it in, we condition it, and then now we have 70-degree air. Well, we need to keep going because that's not cold enough. So now we take that 70-degree return air and we treat it again. We condition it again past the coil. And then now we might have 65-degree air. And we keep doing that and keep doing it until we have the best possible treated air, the best possible temperature of treated air, and we reach set point. So this is the perfect solution to the problem of heat in your home. But again, we don't blow cold air in, we remove heat. Heat pumps reverse the flow of refrigerant to provide heat using a reversing valve. So when you flip this cycle around, your evaporator is now your condenser, and your condenser is now your evaporator. And basically both are just a heat exchanger. So if we think of the evaporator coil in heat pump mode and heat mode, if we think of the evaporator coil as a heater, right? It's going to be hot refrigerant, lots and lots of hot refrigerant. That's going to very easily, with a blower blowing past it especially, heat a room up, right? Because then we're adding heat to the room instead of removing it. So very important to remember that if you hear the term heat pump, it's no different from an AC whatsoever, other than it has a reversing valve to make it capable of reversing the flow of refrigerant. Refrigeration equipment typically uses a pump down method using a liquid line solenoid. We talked about that. The compressor only ever sees vapor refrigerant. I will beat this dead horse until it can't be beat no more because it is so important. Don't be overcharging units. I would much rather you undercharge a unit than overcharge it, for sure. Pressures aren't everything. For decades and decades, we only had pressures to go by. And then if we happen to have someone kind enough and smart enough to teach us the calculations, yeah, we could get our superheat and our subcool and our saturation temperatures. But that was very few and far between. And most of the time what ended up happening is our lead taught us to feel the suction line. And if it's cold, we're ready to roll. Now we know better. Now we can't be having that, because even if you just had an excess of refrigerant, that could make that line cold, right? We have to be very, very careful that we're testing and we're not just guessing. And again, pressures aren't everything. Pressures will only tell you a couple of things. They will tell you if your system is relatively flat on refrigerant, if it's almost empty. They will tell you whether you have a restriction. If you have, lots of refrigerant on one side of the system, you might see a higher head pressure on the condenser side, whereas you'll see a very, very low head pressure on the suction side. But those are two of the three things it can tell us. And the third is just if it's broken. It can tell us that it's equalized. If it's out on thermal overload, or it's completely junk, or it's not turned on, pressures can tell us that by being equal. Those are the only three ways that those pressures are going to help you. Whereas these temperatures are all pieces to a puzzle that could have infinite outcomes. Make sure you're measuring. Please, please, please. All right. Go ahead and put your questions, comments in the chat. I'm going to go over those if we have any right now, but if not, I'm going to teach you guys a few history facts just to make this a little bit less, monotonous. All right, let's see. We have that HVAC Mac. Thanks for being here, Mac. Miss Jen, do your thing. Always, always. Andy from Encompass. We have Andy. Oh, there is no audio. I had to learn this the hard way. When you include yourself in a PP, it's on mute. Mine is unmuted, Andy. Hopefully we actually do have audio. I am not muted. I hope there was audio. Yeah, it says that I do have audio, so hopefully we do. And Valentino is Jennifer. Okay. The more you know. The first air conditioner was invented. Actually, let me try this real quick. Yeah, everything's right. And it's saying that my mic is working. Okay. Anyway, I'm going to keep going and I will talk to Andy after. Hopefully this has audio when we get back. All right. Refrigeration theory. So the more you know. The first modern air conditioner was invented by Willis Haviland Carrier in 1902. Mechanical refrigeration was invented by the godfather of refrigeration, Mr. John B. Gorey himself. Willis Carrier invented air conditioning to help printing companies out because the humidity in the printing company was becoming so great that they weren't able to print and then keep their papers stacked. They were running out of room. So those papers would stack up, they would stick together, all of the printing was ruined. So that's why Willis Carrier invented air conditioning. And it worked. It worked great. And then it became the norm in every household in the entire world. So mechanical refrigeration, however, is where Willis Carrier got the idea for air conditioning. He thought, okay, I need to fix this printing company. If John B. Gorey can invent refrigeration, if he can cool a room based on these methods of heat transfer, I can do it on a wider scale, right? So John Gorey was only doing this because medical patients needed to be kept cool in hospitals. So what they would do is they would go cut these massive hunks of ice and they would put them in the hospital and they would blow fans past it to keep these dying patients alive and to keep, medicine cold. And after a while, that became really, really hard. They had to truck that ice in from miles and miles and miles away and then get it to whatever floor in this hospital it needed to be on. This was not an efficient method at all. So what did John B. Gorey do? He needed an artificial way to make ice because we weren't quite there yet to a point where we're like, we're not going to use ice for this. We knew ice worked. So we were just going to keep doing that for a while. So John B. Gorey actually created a system using ammonia, using absorption to make ice. And when he did that, it was probably one of the biggest foundations of everything we know today that we ever could have gotten to. And if John B. Gorey hadn't have said, it's too hard to truck this ice in, we need to make ice, we wouldn't have ice machines today. We wouldn't have lots of things that we have today. We wouldn't have air conditioning. We wouldn't have any of these things. We wouldn't have refrigerators. The first fully air-conditioned home was owned by Charles Gilbert Gates in 1913, and it was fully air-conditioned. I cannot promise that we didn't have cold spots and hot spots, but it was fully air-conditioning. Without the invention of air conditioning, many medications would never have been invented. In turn, some diseases wouldn't have been cured. So if we couldn't invent things like penicillin that have to be kept in the fridge, right? If we couldn't invent things like that, we couldn't cure a whole lot of diseases and infections. And so there would be a lot more dead people right now. Air conditioning saves lives. It saves so many lives. If you think of pharmaceutical plants and pharmaceutical labs, we've got to keep that stuff cold. We can't have it rotten out. Then you go and put it in a patient's IV and then the patient dies from it. We have got to make sure that we're maintaining a dialed in temperature for these medications. And without them, they wouldn't have been made because we wouldn't have had a way to keep them cold. Thomas Midgley Jr. invented the first synthetic refrigerant, and that was Freon 12. It was a CFC, chlorofluorocarbon. It was the worst for the environment, obviously, but it was a stepping stone to get us where we are today. The Roman Empire used the HVAC, I'll tell you what they were, to heat homes and bathhouses until the invention of modern heating. So we are talking generations they used HVAC. And HVAC was basically a series of tubes, you could call them. They were more like mini chimneys, and they would hold heat. So you would start fires under them. They would hold the heat in the tube, and then they would be positioned under the floor, which heat rises. So heat would rise from these tubes and keep the floors nice and warm. And they used this as a way to heat their homes and their bathhouses over and over and over and over again. And it also kept the bathhouses water warmer, and you used less energy to heat them. So worked out pretty well. And they used that again, you guys, until the invention of modern heating. That's pretty crazy. The Persian Empire invented the yaktal, which they make ice, but they also keep ice from melting in the middle of the desert. In the middle of the Persian desert, there are these massive, I'll show you them. Actually, I have a slide here. Massive clay structures that literally you could house like a village worth of people in this thing, but it is solely made to use physics, to use the temperature of the desert, the natural temperature of the desert, to create ice and then to store it. And inside there are all kinds of moving parts, and it's really great. And I'll show you guys that someday, but it's very, very cool. Down here is the ice maker, one of the ice makers that John Gorey made. It's actually visible. You can go and visit it in the John Gorey Ice Machine Museum. And then down here, we have a picture of the HVAC, a better kind of understanding. So the fire would heat the tubes would heat the floor would heat the space, and we have all the methods of heat transfer happening. Up here, we have Mr. Willis Carrier himself. We like to call him Daddy of AC. He is with one of his first models. It is not the first model, but is one of the first models that is now housed at the Smithsonian Museum. Pretty cool. I would love to go and see it someday. I haven't made it. And then here we have a jug of good old R12. Again, one of the worst inventions as far as our environment goes. We actually blew a hole in our ozone by using that because it contains chlorine. So chlorine in refrigerant, every molecule of chlorine kills 100,000 molecules of oxygen, or up to 100,000 molecules of oxygen, of ozone. Well, of oxygen, but ozone is made up of 3 oxygen molecules. So it can kill a whole lot of ozone. And that's what ended up happening. So we came into the Montreal Protocol, we came into the Clean Air Act, and we said, no more of that. We can't be having that. And now that's what led us to the refrigerants we have today. But that was the first synthetic refrigerant. All right, I'm going to go ahead and stop sharing. I am really hoping that this has audio. really hoping this has audio. If it doesn't, we will have to go ahead and re-record, but I'm going to go ahead and end the live now. Thank you all for being with me. If this does have audio and you do have questions, please make sure you reach out to me. You can reach me at HVAChick anywhere. HVAChick Coalition, HVAChick Jennifer. Thank you all. Make sure you go to Encompass Parts. Make sure you download that Easy Stack. We love Encompass. Bye. Thank you.